Today we are going to discuss weekly contest 494. So without any further ado, let's deep dive into the questions. So the first question was construct uniform parity array. Okay, and right, and we are given. Let me read the question. We are given an integer array nums of n integers, and we want to construct an integer nums2. So nums1 is given to us, and we need to construct nums2 such that all the elements in nums1 is either odd or all even. Okay, and we are given two cases for each index I. We must choose exactly one of the following. So we have been given two options to construct nums2 from nums1. So either we can do nums2 of I equals to nums1 of I, or the second case is we can make nums2 of I equals to nums1 of I minus nums1 of j, and j is not equals to I. All right, and we need to return true if it is possible to construct such as array, otherwise we need to return false. Okay, so let's copy the question and let's see. By the way, let's go through the example test cases as well. Right, so nums1 is given to us as this 2 and 3, right? And if we see, right, so if you try to convert this to all even, right, what it will be 2, and this one will be 2 minus 6, so that's not possible. So if you try to convert all into odd, so this is odd, right? And if you subtract 2 from 3, we'll get -1, and -1 comma 3 nums2 is all elements are odd, so this is true. And 4 comma 6, all the elements are already even, so it is returning true, right? The constraints are length of nums is up to 100, and nums1 of I elements of the nums are also less than 100. Okay, so let's discuss, right, what will be our approach. So yeah, all right, so we are given, right, nums1, it is already given to us, and we need to construct nums2, and we have two options, right? Either, so we can either make nums2 of I is equals to nums1 of I, or the second case is nums2 of I is nums1 of I and minus nums1 of j, where j is not equals to I, right? So what will be my intuition for this problem is, let's say we are given an array, right? I will try to make two cases, right? Either I can make it odd, all odd, or either I can make it all even, right? Okay, so if I try to make it all odd, right, so in case if the number is odd, already odd, so no issue, right? So no issues. If the number is even, if nums of I is even that means nums of I is even, in that case it's an issue, right? And if you want to make it odd, how do you make it odd actually? Okay, so I need to find another number, because we know, like, if you want odd, right, so if there is a even number and if you subtract a odd number from it, you will get a odd number, right? Like 5 minus like, let's say this is 6 minus 3 is 3, right? So I just need to find another an index. So I just need to find an index j, such that j is not equals to I. So j is not equals to I, and nums of j is odd, right? So that will be my approach in case if I want to find if it is even or not right? And for that, what I can do is, since the constraint are very less, right, I can run a for loop. So I can run a loop to check it, run a loop for j that runs from 0 to n minus 1, and j is not equals to I if number is even, number is number is odd, sorry, number is odd, then it's true, right? Else will return false, like not possible. Now let's move to the second case, right? In this case, if you want to make all the elements even, right, all the elements even, in that case, if it's even, if the nums of I is already even, if nums of I is already even, in that case it's not an issue for us, okay, so no issues. If nums of I is odd, right, we need to make it even, we have to convert to even, right? How do you make an odd number even, right? So if there is an odd number, and if you subtract an odd number from it, you will get even, right? Let's say odd number is 3 and you subtract 5 from it, you will get -2, which is even, right? So in both the cases I need to find find an index j such that j is not equals to I, and nums of j is equals to odd. If I am able to find for every index, every conflicting index, then my answer will be true, else it will be false, right? So that was pretty much easy question. So let's have a look at the solution, right? So I'm trying to make either even. So parity represents what I'm trying to make. If this means 0, that means I'm trying to make all the elements as even, and this being 1 means I'm trying to make all the elements as 1, as odd, right? So let's say for this, so I'm going over this, I'm iterating over all the elements of the array, right? And I'm saying if the number is, like, if I'm making parity as 0, so if the number, that means even, right? If the parity is 0, it means even. So if number is even, that's not an issue, else I will have an answer as false. I will iterate over the array, and if I is not equals to j, in that case I'll find out the difference, right? If I'll find out the difference, and if the difference is equals to parity, will it the answer is true, okay, else will return false. Like if we find the same difference, that means it's like odd number, and hence we have found an answer, so we'll break. If we are not able to find after this loop continues, that means there was no possible odd number, and in that case we'll return false. So, or if it's true for all the cases, then we'll return true. So that's pretty much for this question. It's a implementation problem, and yeah, so that's it for this one. In case if you have some doubt, let me know. Now let's move to the second question, right? And this is a follow-up for the first question. So the question is almost the same, just that this condition is changed, right? So we are given an integer array nums1 of n same, and we need to make nums2 such that all the elements are either odd or either even, right? For each index I, we need to choose exactly one of the following, right? So I can choose nums2 of I equals to nums1 of I, or nums2 of I is equals to nums1 of I minus nums1 of j, where j is not equals to I. They're the same thing, right? Just that it's given like nums1 of I minus nums1 of j. So the element that I'm gonna choose, right, whichever index I'm gonna choose, that must be smaller than the index. So if I'm choosing 4, right, I can't choose anything greater than 4, because 4 minus any value greater than 4, it is not going to return me 1. I have to choose a value which is less than equals to 4, right? So that's the thing to note in this one. So let's see, like nums1, this one, right? So 1, 4 and 7, right? So the output is true, because if you see, like if I try to make all the element as odd, right, so 1 is already odd. So if I see for 4, if I subtract it with 1, right, I will get 3. So 3 and then 7, so all the elements are odd, and thus the answer is true. For this one, if you try to make it odd, right, if you see, right, 2 and 3, but let's see this one, right, so the answer is true because all the elements are even. For this one, let's see, okay, 2 and 3, right? So what I'm gonna say is, okay, let me see if I make extension. No, I don't have one. All right, no worries. So if you see, if I try to make all, let me copy it, and then we'll have a look at this. right? So this example, right? So let's see this one. We have our array 2 and 3. If I try to make all the element as odd, right, in that case 2 is an issue for me, yes. So I need to find a number, and nums1 nums2 of I is equals to nums1 of I, or nums2 of I is equals to nums1 of I minus nums1 of j, such that this value, if I say this as a value, such that the value is greater than or equals to 1, right? So if I pick 2, for 2 can I pick anything? If I pick 3, right, for 2 if I pick 3, 2 minus 3, which is equals to minus 1, and minus 1 is not greater than greater than equals to 1 is false, so this can't be done, right? So for this case we can't make it, hence we'll return from here that it's not possible to make it odd. Let's see if we're able to make it even, right? So in this case this 2 is not an issue for us. If we move to 3, 3 is an odd number, which will be the issue. So what I'm going to do is 3, if I subtract 2, right, I'm going to get 1. 1, is it greater than or equals to 1? Yes. But is it even? No, it's an odd number, hence we can't make it. So that's the reason why the final answer is false, right? So what will be our approach for this question, right? So let's see. And okay, so you see, like, the second condition what it was mentioned, right, this one. So let me first. Right, so in this case if you see, if I need to pick anything, right, so it must be the value. Let's say if I'm picking this case, right, this one, or look properly at this one, what happens is, let me erase this, and if you see, right, so whatever this value is, value which is equals to nums1 of I minus nums1 of j, and this must be greater than or equals to 1. That means this value should be smaller than this value, right? So I'm planning to sort the array, right, so that if the array is sorted, right, and let's say I'm at this index, right, I'm searching for this element, so I know I can only pick these values on the left, because this value will be greater than this, and in this case the value will be the value will be negative. So nums of I minus nums of j will be negative, which violates our condition. Hence the only option for us will be to consider something from this part, so that j will be on this part and I, such that nums 1 of I minus nums 1 of j, and this will be greater than or equals to 1, right? All right, so this is the this is one thing to note, right? Now second thing, in this case also we can try to make two conditions. Either we try to make all the elements as odd, or we try to make all the elements as even, right? So in the case if it's an odd number, right, if it's odd, right, let's say it's odd, this is odd number, so 3, let's say it's 4, this is 6, and this is 9, let's say this is the number. In case if I want to make let's let it be like this, let the array be like this, 3 4 6 9. I guess it will be better with this example. So if I want to make it all odd, right, so what I'm going to do is, so it's already an odd, okay, if I see here it's not an odd number, right, it's an even number. an even number, if I want to make it odd, right? If I want to make it odd, how can I do? It is even, and if I subtract any odd number from it, which is less than this number, then I will got an odd number. Okay, so I will keep a variable odd count, right, which will store how many odd numbers I have seen so far before this index, right? So if you see at this index, so when 3 was there, we incremented this to 1. So now when we commit 4, we see it's an even number, right? This number is even, and if I want to make it odd, so this number is even, and if I want to make it odd, I will have to find an odd number, because even minus odd is odd, and I see there is already odd number on the left, so our answer will be true for this one as well. Now I come here 6. Okay, 6, what can I do? I have already seen 6 minus 3, which is 3, it is already, it's also there. 9 is already odd, so that's not an issue. So that will be the condition for an odd number. So what is the main logic that we have seen? If odd, no issue, right? But if it's even, check if we have found an odd number on the left of I, right? If index is I, if this index is I, then find a odd number on the left of I. So that will be the condition for odd number. How do we check for even? Now let's go for even one, right? Let me change the pen color. So if I want to make it even, right, 3, 4, 6 and 9, right? So this is an issue, right? And this will return as -1, we can't. So let's take some other example to understand this. Let the array be 2. Okay, let here be 2. So if I say this is an even number, so it's not an issue for us. And if I see there is an odd number, right? Wait, now see, for a number, if there is an odd number, right, in this case, if the number is odd, then we have to make it even, right? And how do we do? Actually, if there is an odd number, and if you subtract another odd number from it, then we're going to get even number, right? Okay, and I don't think we even need this case, because it will already give true. So let's see if okay, so this case it's giving wrong, because okay, so if the array is already even, in that case we don't need to. Okay, but anyway, this is just to check if all even. Okay, if we don't need it actually. Right, let's try this. I think this should work, because we don't actually need that case, but if you need, like, we'll accept. Okay, yeah. So if you want to make all the element as even, right, if you see any odd number, right, there's no way you can make this element as this, all the number as even, right? So in this case, what I'm going to do is I'm going to check, is all the elements even? If all the elements is even, in that case I'm going to return as true, else I'm going to return false, because there is no way. So if you find any odd number, right, so you'll have to find another odd number before. Okay, so if I find any odd number here, let's say 3, and I need to find another odd number on the left, let's say here odd number is 1, and then if I subtract 3 minus 1, then I will get answer 2, which is even, right? But for this one I need to find some other odd, right? So it will be a deadlock, and we can't find anything. Like for the extreme left one, there won't be any number and hence this will never be able to make it even if there is any odd number present. Okay, so this is main thing to check. If it's odd, then it's not an issue, but if it's even, we need to count how many odd number we find on the left of I, if we are able to find at least one, right? So this is the solve odd. So I will keep a odd count, okay? And I will iterate over the nums. If the number is even, right, that's where the issue is. And if the number is even, we'll check if the odd count, if it is 0, in that case there is no odd number on the left of I, and in that case we'll return -1, else we'll increment the odd count, okay? And if we are able to find for all the element, if the element is either odd or we find an odd number on the left of I, in that case we return true, right? For the even number, that's I mentioned, right, we don't need this as well. Just check if all the elements in the nums is even, right? And we need to sort the nums as I discussed, because we need to find an index I on the left and j on the left, and nums j must be smaller than nums of I. That's why we've sorted this. So that's pretty much it for this problem. A follow-up of the Q1, but not much to take into consideration, just that we need to sort this, okay? Now let's move to the third case, the third problem, right? And this is actually a I'll say a good problem, because initially you are not sure, you might think like I need to go for greedy or something, but yeah, let's discuss the problem first and then we'll understand what's the intuition behind it. Okay, so minimum removal to achieve target ZOR, right? We are given an integer array nums and an integer array target, okay, and an integer target, okay? So array nums is given to us and a target is given to us, and it is also given like we may remove. So let me first take this, right, and let me paste it. So what is given to us, you see, right? This nums is given to us, this nums and this target, and our final goal is to remove element, is to make the nums, the bitwise OR of all the elements that are present in this nums equals to target. For all element that belongs to nums, right, the bitwise ZOR is equals to target, right? So, and if it is not possible to make the achieve target, we can return -1. And the power that we are given in this question is like we can remove elements from the nums, and we need to return the minimum number of removals that we can do to obtain this target. So in this case, if you see, right, 1 and 3, so nums, if I do bitwise OR of 1 and 3, I'll get 2, right? Bitwise OR of 1 and 3, so 1 is this and 3 is this, and if I say this is 0, so we know the bitwise OR, right? If it's even count, then it will become 0. If it's odd count, it will become 1, right? So it will be 2, and this is equals to 2. So we see 2 elements are needed, and so we only needed to remove this 2, so hence the answer is 1. There was also another case, right? If you remove 1 and 3, that the number it's remaining itself is 2, so 2 and bitwise OR is 2, so which is true equal. But in this case we need to remove 2 elements, 1 and 3, and hence since we asked the minimum number of removals, the answer is 1, this case, not this one, okay? If you look at this 2 and 4, right, and the target is 1, if you see 2 and 4 and target is 1, so 2 is like this, right, and 4 if you see this, so if you do bitwise OR, right, 1 1 1, so this gives us 5. If you remove this one, like this is giving us 5, like if you take both, if you remove this one, so bitwise OR is 4, right? If you remove this one, the bitwise OR is 2. In none of the cases we are able to make the target, the bitwise OR of the element as 1, hence we are returning -1. Okay, and in this case the nums is 7, and this is already equals to target, and hence we are returning 0. Okay, so what was my initial approaches? Okay, since we are given nums, right, we are given nums, let's say some x1 x2 dot up to xn element, right? I was thinking like let us understand with this one, right? The example case 1 2 and 3, right, and target is 2. So what I was thinking is, let me first write this and then 2 and then 3, right, this, and I was trying like, okay, and target needs 0 1 0, right? So it means I don't need this bit, right? So I don't need this bit set. So I was thinking, how is it possible, like if I think of greedy approach, right? So if I turn this off, like this one, if I make this one as off, can I, what is the, for this one, if I need is to be 0, it's already 0, right? So that's not an issue, but this one is also 0 and this one is also 0. So if I take all the three, it's not possible. If I try to somehow remove this one, right? Because I was thinking like, can I go for greedy one, like greedy approach, like somehow think in this term, like, okay, what is the, which one can I remove? Like I was thinking like, if I can really think in any element that I can remove. So I was thinking, okay, if I remove this one, then it will be 0 0 1 0 1 0, and in this case it will be 3. But that's, we're not sure which one actually to remove or which one to not remove, and greedy was not leading to any result. Because maybe, let's say, if I somehow remove this one, if I somehow remove this one, this element, so in that case I'm getting 3, which is not the desired answer. But let's say if I remove this one, in that case what I'm going to get is 1, which is also not desired. So if I remove this one, so I'll get 0 1 1, so I'll get 1 1 0. This is 2. But again, then the issue is like, which one to pick and which one to not remove, right? It's pretty challenging to arrive greedily at any point. But in case, if you were able to find anything, do let me know in the comments. I love to know your approach, right? So when I was not able to find out or figure out anything, then I thought, let's have a look at the constraint. And luckily I see like the constraint, and nums of length is 40, right? And then nums of I is also less than 10 to the power 4, and target is also 10 to the power 4 in the range, right? So then I thought, okay, why not do this, like take all possibilities, like then my approach was consider all possibilities. Consider all possibilities. Why? And why? Because if I consider solve, right, then if I need to consider all possibilities, like let's first understand how, okay, and then we'll understand why. Okay, so I had this, right, 1 2 and 3, right? Then I thought, okay, what if I take 1, this is not take, okay, and the element currently we are considering is 1. If I not take 1, so this will be 0 0 1, this will be 0 1 0, and this will be 0 1 1, right? If I not take 1, so my current bitwise XOR will start with current XOR is equals to 0, okay. If I not take 1, if I take 1, right, if I take 1, in that case my bitwise XOR will be this bitwise XOR, right? And in the next case, this element I move to this, so this index, I have the option, right, 2. If I don't take it, so it will be 0. If I take it, right, so 0 XOR bitwise XOR 2 is this, right? Then similarly in this one, if I see, right, if I don't take 2, then it will be 0 0 1, it's 1. And if I take 2, right, then 0 0 1 0 1 0 bitwise XOR we need, so it will be 1 1, and this will be 0, right, it's 3. Now the element is 3, right? If I don't take it, it's become 0. If I take 3, right, so 0 XOR 3, it will be 3. For this one, if you see, right, for this one, if you see, right, if I don't take it, it will be this. If I take it, so the already we have this, and if we see 3, right, in that case if we do XOR, it will be this, right, 0 0 1. Similarly for this one, if I don't take it, right, then it will be 0 0 1. If I take it, so 3, right, this, so it will become 0 0, right, this one. Similar case, if I don't take it, it will be same. If I take it, right, so we already had this, and if we take 3, right, it will become 0. And at the end, what I'm going to think is there anything which has become equals to 2, right? So no, oh yeah, no, yeah, no, No. All right. So these are the two cases which are leading me to some solution, right? This is one case, right? And second case is something like this, 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 right? And how do we find the answer, right? So if I don't take it, that means I'm removing it, right? If I don't take it, it means if I'm not taking it, I'll consider how many elements I've taken, 0. If I'm on the right, that means I'm taking it, right? So I'll consider as 1. And if I'm on the left, that means I'm not taking this element, so that means 0. So this part actually represent, so I have not taken 1, so 1 I have not, so this part, if you see 1, 2 and 3, this represent this red part, it represent I have not taken this 1, I have taken this 0, this 2, and I have not taken this 3. Okay, however this part, if you see, right, this yellow part, it represents I have taken this 1, I have not taken this 0 or this 2, and I have taken this 3. So that means in this case how many elements I am taking? I am taking 2 elements. In this case, how many elements I am taking? I am taking 1 element. If I am taking 1 element, that means how many elements I have to remove, right? I have to remove n minus how many elements I taken, right? That is 3 minus 1, that is 2 elements I am removing. So yeah, 1 and 3. In this case, how many elements I am removing? 3 minus 2, that is 1. And which is the element which is getting removed in this case, which is 2. So I this is a better solution for me, right? This part. Yeah. So that was how I thought, why not consider every possibility. I tried taking all the possibilities that is even possible, try to include or not include it, and at the end I will check, am I able to reach, if am I able to make the current or XOR equals to the target. If yes, then I will see how many elements I have taken. If no, then I will say, okay, if it is not possible, in that case I am going to return something like very small number, like -1e9, 1e5 or something, and I will not consider this actually. So in those cases where the bitwise or at the final step is not equals to target, I will just discard those cases. So finally we had only this and this case where I had the answer. And so why did I even think of this solution, right? Why? Because if you see the constraint, right, if you see the constraint, so in the constraint n was equals to 40, worst case, right? I am considering worst case time complexity, and nums of I is less than equals to 1e4, right? And target is also less than 1e4, so less than 1e4, right? So I was thinking like, okay, so if you see in the solve function, right, which all things are changing, right? If you see this index is changing, right? Because for every position, every next step I'm taking a new index, right? For the first I'm going for 1, then I'm going for 2, for next I'm going for 3. So this index is changing, right? And what is my current XOR value? So this values currently that we had, that is changing. And in worst case, if let's say if this if say your number is 8, right, 7, let's say your number is 6, and in worst case what is the value that it can reach, right, with current XOR? Let's say some other numbers were there that had this, so in worst case also it can only reach 7, right? So it means it can only reach at worst case something like the maximum set bit, whatever is the maximum set bit, we do power of 2 index, which is the max index, and then -1, right? So if it index is 0, 1, 2, 2 power, this will be what? This is the third index, right? 2 power 3 to the power 3, which is 8 minus 1, 7, right? In worst case also it can only reach up to 7. But if you don't want to do exact approximation, we can take something like 1e5, because we know at worst case also it will never be able to reach 1e5. And that's what even I did. Like I didn't want to while I was solving it, I didn't want to approximate too much, because even with this constraint 1e5 and 40, so that will roughly be 4 into 10e 1e6, which is still what Leetcode allows. So that was what I was thinking. So yeah, so that was my initial approach on how I'll solve the problem. So let's write the pseudocode, right? So I'll have one solve function, right? And I will take index, and I will take what is my current XOR, right? So one will be if this index is greater than or equals to n minus 1, where n is the size of the nums array, right? Then I will check if current XOR is equals to target, right? In case if it's equal to target, I will return 0. In case if it's not equals to target, that means I can return something very large negative. That means this path doesn't give us a result, like this path, like this one. If you see, if you start from here, here and here, this part doesn't give us any solution, so we'll return minus 1 something like that. Okay, now we have two options, right? If I take it, right, so I am including 1 to indicate that I have taken one element, and then I'll move to the next element. And then current XOR, it will be, I will have I have taken this, so this current XOR will change, and I will have nums of index, right? Like if you see, if I take this, right, if I take 1 here, right, the element here that we're considering is 2, so 0 0 0 and 0 1 0, so the current bitwise XOR will become this 2, that's what representing, so that is what this current XOR will become, right? Else case will be if I don't take it, so it will be not take, this will be 0 plus solve, so index will move by 1, right, and current XOR remains the same, and at the end I'll return maximum of this both cases, all the possibilities that we had. So this will cover all the possibilities that we make, right? This is the pseudocode actually for this one, and of course we'll do memoization as well, so that it doesn't pass it passes the constraint, the solution, and we don't get a TLE or something. So now let's move to the solution. I guess the writer is pretty clear, so let's move to this. Okay, so as I mentioned, right, I will have a DP, and DP, the size of DP, since the changing parameters are index, and this current XOR, which in worst case will be 1e4 1e5, which anyway will be less than 1e5 since I showed you the approximation, right? So I'm taking 1e5, but yeah, you can do the approximation, and you can do like this one that I mentioned, right, power 2 and index minus 1. So just find out the maximum MSB and just 2 minus 1, power it 2 and 2 minus 1. Okay, so this solve function, this nums index current XOR and this target, just to check it's not changing, it's not a changing parameter, so we don't need to take it in our DP, right? We'll just find the size of nums. If this index is equals to n, right, in that case I'll check if the current XOR is equals to target that I mentioned, right, at this index. If the current XOR is equals to target, in that case I'll return 0, else we'll return some very large number, right, 1e5 or minus 1e5 or something. If I take minus 1e9, I will have to, like, I didn't do it because it will again need long or something. So but yeah, you can easily do it 1e9 if you take this long, because at the end I took long. So the case one is if I take it, right, so I will add 1 to my answer and then solve, call the same function index plus 1, and current XOR will be current XOR and bitwise XOR nums of I, right, and then the target same. If I don't take it, it means I have not taken this, so it will be 0, the current contribution will be 0, and solve nums index plus 1, index will move by 1, current XOR will remain the same, and at the end I will return the maximum of take or not take, and I am doing that memoization here with index and current XOR. So if it is not equals to minus 1, in that case I am returning it, and at the end I am also storing the result in this vector DP before returning the answer. So this is just classic meme set to fill the DP array with minus 1, and I am finding the answer, calling this solve function, whatever the answer is it is earning, right? If the answer is less than 0, that means there was no possibility where I could have reached a solution, and hence I was returning minus 1. Okay, if the answer is less than 0, that means it's not possible. right? But if it is possible, right, in that case I'll return n minus answer. So just as I mentioned, right, in this case as well. So here how many elements I have taken? So I have taken only one element, so that means n 3 minus 1, which is 2. But in this case, if you see, it's like I have taken two elements, so 3 minus 2, which gives us 1, right? So yeah, that's pretty much for this question. I Yeah, just have a look at the constraint before, so the learning was for before you jump to something, like have a look at the constraint so that you know which direction to think of, right? Okay. Yeah, so let's move to the next question, and in case if you need any more help on this, yeah, feel free to let me know in the comments. I will help. Okay, so this was a classic uh, lead code question, and it's one of the good questions, right? uh, so this type of questions are very common in lead code contest, like question 4, like where you need to count sub arrays like that, and the constraints are usually are very high, like and will be 10 to the power 5. So the brute force solution order of n square usually fails, right? But yeah, so we'll be discussing this today, how we solve this type of problems and what is the usual thing that we should look at. Okay, so let's read the question. We are given an integer array nums, right, and a subarray is called good if the bitwise or of all its element is less than or is all the bitwise or of all its element is equal to at least one element present in the subarray. Okay, and we need to return the number of good subarrays, and they have mentioned, right, what is the good subarray. A subarray is good if the bitwise or of all the elements, right? Like let's say if this subarray, if we take, right, the bitwise order of this all the elements in the subarray is 6. Is 6 present in this array subarray? No. So this is not a good subarray. If you see this, right, this one 2 and 3, what is the bitwise order of this subarray? This is 2 or 3, this is 3. And is 3 present in this? Yep. So 3 is present in this, hence the answer is yes. So this is like we'll do for every element, every all the subarrays, and at the end we'll count how many subarrays were part of the answer. So this is the part of the answer, this is the part of the answer, this one is, this is not, and this is not, hence we'll return the 4. Answer is 4. Like similarly for this one as well, right? And the constraint is 1e5, and nums of I is 1e9, right? So how do we actually solve this, right? Let's go to the screen, right? Okay, okay, so we're given this subarray, right? Like which one? Let's understand 4 2 3, right? First let me remove this. Nums is 4 2 3. If I take 4, the all the single subarray, this 4, then I can take 4 2, right? Then I can take 4 2 and 3. Then next is 2. If I start at this, then I can take 2 and 3. Then I can start with 3. Is this a good subarray? Yes, because sub bitwise OR is 4 and 4 is present. Is this? Because this is 4 and this is 2. The bitwise OR, oh, okay, the bitwise OR will be 6, which is not present, so this is not an answer. If you see this, so 1 0 0, 2 will be this, and 3 will be this, right? So this and the value is 7. Is 7 present in this? No. So answer is not, no. If this is 2 and 2 is present, yes. 2 and 3, so 2 3, so it will be 3, and 3 is present, so it's an answer. This is an answer as well. So the answer for this problem, as we have discussed, right, this one, this one, this one, and this one, which is 4, right? Now how do you actually think, right? You can't do like this, like you can generate all the subarrays or check for all the subarrays, right? So I'll give you one trick. Like usually when you get a question like where you need to count the number of subarrays, right? And like you can't go for n square, right? So what you try to do is, like let's say this is a subarray, right? And if you are at index this, right, this index, currently at this index, what you try to do is you try to find an index such that up to this index you will be able to contribute. Like let's say up to this index, the subarray, this up to we try to expand on the left, right? On the left, if you expand as well up to this index, our constraint or condition is valid, so we'll say this index is left, right? Similarly, we try to expand on the right, up how much I can go, right? So let's say this is the index up to which I can go, and this is right, right? Okay, so this is usual thing that we try to do, right? We try to think of, okay, so we go like this, and at the end our answer will be how much the left has contributed, right, and how much the right has contributed. Based on this, we do something like based on question, right? Calculate answer plus equals to contribution. Like this contribution is different for based on question. Like for this part it will be like if I had an subarray like this, and I had like, okay, this is the parent on which I am trying to expand, and I am seeing like, okay, 1 2 and 3 elements are there on the right, and there are 2 elements on the right. So this is right, let's say, okay, and this is left. So for this particular case, we can see like all the subarrays that has this element x. So x, then x can have x and this one, right? Then x and this one. Similarly, I can start with this and this. I can start with this and this up to this, and similarly I can start with this and this up to this, right? And the other case will be if I start here, like here, and I end it here. I start here, end it here. Similarly, I start at this index, right, and end at this index. I start at this index and end up to this, and at the last I start this, like I start here and end here, start here and end here, right? So all this, if you see, right, if we add all this, answer is equals to this contribution. So if you see 1 2 3 4 5 6 7 8 9 10 11 and 12, right, which is equals to, on the left how much did I have? 1 2 3, right? So left is, so it will be equals to, what is the value of I minus left plus 1 into right minus I plus 1. You see, right, this is what our course answer is. So on this I have 1 2 3, right, and on this 1 2 3 and 4, and this 1 2 3, so 3 into 4, 4 into 3, which is equals to 12, right? This is the thing, like, okay. So yeah, this is one thing that we observe on this question. So yeah, keep a note, like, right, in cases where we can't do an n square solution, right, order of n square, fix the index, right? For every index we try to expand the maximum we can on the right and maximum we can on the left, and we somehow calculate if these two are done. So based on the question, we'll calculate answer plus is equals to contribution, like which these two left and right makes, left and right, how much these two can contribute. We generally use this one, so this is something very important to note, right? Now for this one, right, particularly, let's see, right? So in this question also we'll do something similar, like, you know what we are given, right? If I'm at this index, let's say this is my index I, if I will say like I need to include this index anyhow, okay, and now I will try to expand on the left. So if, let's say, if this index is this, right, 4, if I find any element, right, if I find any element on the left which has a bit which is set other than this bit, so if it has something like this bit is set, that means the bitwise or if you take, right, for this two part, it will not be equal to this element, right? So I'm trying to make all the elements such that if I take this, the bitwise or will remain the same, this one, right? So I'll try to expand on the left till I can expand till that element whose bits, like let's say if it has bits, right, some bits, the bits that are set is also set in this element parent, let's say they call it parent, right? So if it has bits set at this, and let's say if it has bits set as here, so all the elements on the left, I'll try to find an index on the left, all the elements on the left will have either this bit set, this bit set, or both bit set, but they can't have any other bits which is set other than this two, like, okay. And at the index where I find this is we have where it is violating this condition, like any other place where the bit is set on the left will break it, and that will be our left, okay. And similar way we'll do for the right as well, right? So the thing is, if bitwise, no, so if bitwise or of left, so let's say if this is left, so we'll say left to parent or index is equal to parent. It will always be equal to parent because it will be only having this bit or this bit set, it can't have any other bit set. So this is the condition, and the condition where it breaks, that will be the one where our left will break. And similarly on the right, it will be like bitwise or of parent, like this is the element which is parent, to right is equals to parent, right? And that is the maximum up to which we can take. Like the next element, let's say if the array is like this and if our right is here, so this means that this element has some bit which the parent doesn't have, like set. So it might be like this, it has this index, this element, it has something like 0 1 0 1 0, anything like. But if you see, like the parent had this bit set and this bit set, but it had this bit set, or even if this is not, like let's say if this element is this, then also like the parent only had this and this bit set, it can't have this bit set, okay. So this is what we are probably trying to do, right? Now our thing is, how do we find, like, okay, if I go ahead, like, okay, this is the parent, right? I can't go like, okay, left, is this possible, okay, left, is this possible, okay, left, can we take this? We can't do, because if we keep going, right, like if we say like from this index to this index, the bitwise or equals to parent, from this index to this index, the bitwise or is equals to parents, and this to this, again the bitwise or is equals to parent. We can't do like this because it's again going to take order of n, and since we are doing it for every element, the bitwise or it will take order of n square, right? Similar things, if I'm doing something on the left, that means the similar thing I'll be doing on the right. So just consider the same thing accordingly, right? So how do we actually do it? Can I do something like binary search here? So that's where I thought of binary search. But how do we take it, like, right? So let's say if my parent, if I'm at this index, that is parent, right? If I say, okay, up to this index, right, up to, I'm considering this up to here. If I say, okay, I am finding the mid something like here, right? If I say, okay, the the bitwise or of this particular range is equals to parent, okay, that means I can go on the left more, right? That means I can go more on the left, I can try to expand my range and I can try to find up to here, right? Something like I can expand, right, using binary search. But if I say, okay, this value is greater than parent, it is greater than parent, right? That means there is some element in this part which has a bit that is not set in the parent. That means I can't take up to this part, so I'll try to that means I can't take up to this part, so I'll try to decrease my range, right? So my range will decrease up to from here, right? So my high will become up to here. I'll try to say, okay, this is not possible, so I try to see in this particular range, I'll try to do binary search. So that's probably we're gonna do, right? But again the question come, okay, if I'm given like this, right? If I'm given like this, like this range, okay, how do I find like what is the bitwise or of this particular range in order of 1 or order of something like log n, right? I can't take order of n to find the bitwise or, because I can't do and calculate the bitwise or, like do from for each element I find what is the bit, we do the bitwise or of this, right? I need to find something like we can give me the bitwise or of a range in a order of log and order of one time, right? So that's where I thought of, okay, we have segment trace, right? So that's one of the requirement for this one, either segment tree. So if you know how segment tree works, you know, like you can get the range, what is the bitwise order of this particular range in order of log n, right? And for this particular question specifically, the segment tree was giving us a time limit exceeded, so I used a sparse table. So yeah, feel free to do this solution. I just copied the template from my GitHub for this particular problem to solve, right? So that's pretty much for this one. How do we find up to which one I can extend? So I do a binary search, right? So yeah, that's pretty much for this problem. I will just have go through the solution, and in case if you find any problem, like let me know. So yeah, this is just the sparse table that you can copy the template. So I have copied it from my GitHub. In case if you want, you can just go ahead and I'll be pasting it in the description, and you can go in this particular repo, and from there you can paste it. I guess there's some internet issue, so let's wait if it loads, or else no worries. By the time it loads, let it. Okay. uh, so this is my sparse table. So this is the template that I've copied. You can feel free to use from the internet, right? So right, I also explain what this last means. So there's an edge case for which I have to add this because my solution was failing in one edge case. So I'll explain what this does. Like, okay, for every index, what I'm going to do is see, this is the left, only how much on the left can I go and how much on the right I can go. For very starting, I'm saying, okay, if I'm doing for this, right, if I'm doing for this parent I, this is the parent, I'm saying, okay, my left is also I. I'm saying, okay, my left is also here and my right is also here. So that means I can only go up to here. Left is I and right is also I. And then I will do binary search to find the range, right? So I'm doing a binary search. So I'll first explain how I'm doing for the right one, right? Let me see. Okay. So if you see, this is the parent I, and this one I'll say n minus 1. This is my high, okay, and this one I will say this is my low. And then I will find a mid, okay. So let's say the mid is here. Let me change the color to indicate that it's mid. Let's say the mid is here, right? So I will say, okay, what is the bitwise or of this particular from query bitwise or, and what is my range will be of this I, and it's not low, okay. So I need to find I from here, because I am taking every element from here. I need to take this, right, from here to mid. I'll calculate, okay. This will give us some value, okay. If this value is less than or equals to my parent value, like, okay, this index I, that is this parent, that is equals to, that is nums of I, it will never be less than equals to, it will always be equals to or it will be greater than. If the value is equals to this, that means in this particular range all the elements have set bits that is already there in the parent. So I will say, okay, my low, I can expand more the right. So I'll say, okay, I'll try to expand my right. So I'll say right is up to here, okay, at least right comes up to here. And now I will do like this is mid, so I will say low will be mid plus 1. Then low is mid plus 1, right is mid, or else case what happens is, if this value is greater, then in case I will have to decrement my high, and high will become mid minus 1, right? That's the typical binary case, binary search. Then high is equals to mid minus 1, right? High will be mid minus. So yeah, this is the same. The low, while low is less than equals to high, mid, and we'll find the value from I to mid, just as I mentioned, right? From I to mid, from here to here. And if the value is equals to nums of I, it means my right is up to here, and I can make low. I'll try to do the expand more on the this part, like this remaining part. So my low will be this part, mid plus 1, else high will be mid minus 1, like as I explained here, right? So this is for the right part. Now similarly for the left part, what we are going to do is, let's say we have this array, right? And this is my parent, that is index I. So I have found out already some right here. So this is the right index. Okay, on the left I need to find for the similarly expand, see what is the maximum I can expand to get the left, right? So what I'm gonna do in the, it's the same case, right? But let me explain this one. So this time my low will be 0, and I will do binary search here as well. High will be equals to I, okay? And similarly I will find mid, okay? And I'll get the value, query, and let's say if this is the mid, so I'll query for this part, what is the bitwise OR of this. So query mid to I, that is parent. If this value is greater than if this value is equals to parent, that is nums of I, that means this particular has if this particular range has an element, and for every element the set bits are already included in the parent, okay? So it means my ends left can be this, so my left will be mid, and I can say I will expand more on this part. So my high will be mid plus 1, so high will be mid minus 1, sorry, mid minus 1, else low will be mid plus 1, right? So that's what I did here as well. While low is greater than high, I'll also explain what this actually does, so go through it, follow with me, right? I'll query it, I'll see if the value is equals to this, that means low is mid and high is left is mid and high is mid minus 1, left is mid and high is mid minus 1, else low is mid plus 1, okay? And at the end I'll just calculate the answer as I explained, I minus left plus 1. So whatever is this minus left, so at the end answer will be I minus left plus 1. So count of element on the left into count of element on the right, so right minus I plus 1. So this will be the answer for every index I, right? This will be its contribution. And but now let's understand. So this was what I coded, and it was failing this case where elements have appeared double, right? Let me explain this, right? So if I say like, right, this element, let's say here 3 is already there, then again comes something like here 3, and then again like something, even if it comes on the right, it's not an issue for us, but for the left part we need to specifically do, because for this part we'll be solving, right, expanding on the left and the right. Because while we are expanding on the right, we'll consider this as well, like we'll for this particular part, right, when we expand, we'll consider like let's say 3 1 3, and let's say this is 2, right? So when we expand for this part, right, it will cover this, because bitwise OR is 3, this also bitwise OR is 3, bitwise OR, sorry, okay, and this also has bitwise OR is 3, right? So when we are calculating right for this, we are covering this, right? So if you see, right, 3 1 3 1 3 3 3 1 3 3 1 3 2, this all are covered while we are calculating the answer for this, right? So if you now you calculate for this one, and let's say if your left ends here, right, if your left ends here, So what it means is like you will again calculate the, for while you are calculating for this, you will take this. So you'll say 3 1 3, right? This is the same thing, right? So you'll say firstly I will take 3, then I will take 3 1, then I will take 3 1 3, then I can take so like 2 is for everyone, every possibility, right? So that's something similar, like we have already included this answers while we are calculating for this one, right? Hence for the left part we'll not do binary search for the entire one. We'll see till we have not find a similar value, because we will check, okay, what is the index on which I have found already 3. If I have already found an index 3, I will do binary search only after that index, not on this, not from 0. Okay, so that is what actually last stores. So initially last is a unordered map. So what I'm going to do is last is initially it will be, so initially it will be -1, right? Initially it will be like, if the element is not found, in that case it will be -1. If it is found, it will be equal to this index. So I need to, if I find mid on this part, right, that means I can't take it. I I will have to find mid on this part, like, so my binary search should be on this part itself. So that is why I will check if my mid, it is greater than this, whatever is the last index, like this last index that I have found, right? It should be on this part. So this is one just check I am doing. So this, yeah, the last, so mid is greater than last, right? This is just one simple check, and at the end I will say, okay, I have found I will update it, I will store it what index I found. So at the end I will say, okay, last I have found at this index, so that if next 3 comes, we do binary search only for this part and not the entire part, because all this will be covered while we were doing for this one. Yeah, so yeah, that's pretty much for this problem. And I think it was a good question to learn about. Yeah, and do remember to, like, the thing that I have told, right? This part, usually we can't do order of n square, so we expand, keep the center fixed, and then we expand on the left and expand on the right, and